So our topic today is the harmonic oscillator. In classical mechanics, this is defined by the potential V of x equals 1/2 kx squared, which can also be written as 1/2 m omega squared x squared, where omega is then the natural frequency of the harmonic oscillator. So in quantum mechanics, this is going to translate into a differential equation. So I take the abstract form of Schrodinger's equation and rewrite it as the equation below, which is then the differential equation that I want to solve. It's convenient to rescale a little bit, as I've done in the next line, and get this nice form, which tells me that the second derivative of psi is proportional to the difference of the potential energy and the total energy times psi. Now, imagine for a moment that I ignore the fact that the potential is a function of position and simply consider a constant potential. So the differential equation I just looked at then has two different behaviors. In the first case, which is when the potential is less than the total energy, which is the classically allowed region, and I'll explain in a minute why it's called that, the behavior of the differential equation is oscillatory, which is to say, if I define k squared as 2m over h bar squared times e minus v, which if e is bigger than v means that the right hand side is positive, so k is then a real number, I get two oscillatory solutions which can also be combined into sines and cosines. On the other hand, if the potential energy is actually bigger than the kinetic energy, then I get a solution which is either exponentially growing or exponentially decaying. And notice that the definition of kappa and k are different, because in the lower line I've taken the combination v minus e, which is by construction now positive because we're in a classically forbidden region where the total energy is actually less than the potential energy. Now, word on this business of classically allowed and classically forbidden. So in classical mechanics, the energy is 1/2 mv squared, the kinetic energy plus the potential energy. And so of course the first term in this is always positive for classical motions where the velocity is real and its square is necessarily positive. So then if you look at that, it's clear that the energy, total energy, also has to be strictly bigger than the potential energy. In quantum mechanics, this condition can be ignored a little bit, as we'll see, and so both regions are allowed when we're solving the Schrodinger equation, although we would never look in the classically forbidden region when we were doing classical mechanics. So if we now put together these observations, for the harmonic oscillator potential we end up concluding that if we're looking at an energy E, which I'm plotting on the same figure where I have the potential energy, then for the region inside the well at that given energy, I'm going to get an oscillatory solution, whereas outside the well I'm going to get a solution which either grows exponentially, or in this case actually more rapidly, grows rapidly or decays rapidly. So for a normalized wave function, I simply cannot have the rapidly growing solution, otherwise I wouldn't be able to normalize it. And so what must be true is that I have to pick my wave function such for an eigenfunction that I get only the decaying solutions outside. Now, the fact that I want the wave function to vanish at plus minus infinity, gives me two boundary conditions. So if you'll remember the square well, we had a finite interval and we again had two boundary conditions. The wave function had to vanish at either end of the well. So now again we have two boundary conditions, except they are imposed on the asymptotic behavior of the wave function as it goes off to infinity. Now if we start to integrate the equation, say starting in the center of the well, we will choose a value for the function, which is psi of 0, say, its derivative, and then the energy we'll have to pick. And the value of the function itself is up for grabs, because that will eventually only be fixed when we normalize the wave function. It's a linear equation, so the overall magnitude is not fixed by the differential equation. So there are two numbers that I have to pick, and there are two boundary conditions that I have to satisfy. So when you have a story like this where you have sort of two constraints, which are which boundary conditions have to hold, and two parameters that you can vary. Generically, you expect that you can only make the constraints happy, the boundary conditions happy, at discrete values of psi prime of 0 in E, and so you're going to get a discrete set of solutions which will correspond to particular eigenfunctions, much as for the square well-be found solutions at particular energies. Now we turn to the task of actually solving the differential equation and finding its eigenfunctions upon imposing the boundary conditions. So to this end, it's useful not to work with the starting variables, but instead to rescale x by constructing a dimensionless combination, which we're going to call xi, which involves a natural length which we construct from the constants of the problem, and then we rescale x in terms of that, getting a dimensionless number. Likewise, we can construct a dimensionless energy, which is constructed by taking the starting energy and dividing it by the natural energy in the problem, which is Planck's constant times the frequency. So in terms of these rescale variables, I have this differential equation psi double prime equals xi squared minus k acting on psi. Now, I want to first look at this differential equation very far from the classically allowed region. So in these scaled variables, classically allowed is xi squared much less than k, whereas classically forbidden is xi squared much bigger than k. It's basically the xi squared is more or less the potential up to rescaling, and k is the energy. So if we look very far from the classically allowed region, we can simply drop k relative to xi squared. So in that region, the differential equation looks somewhat simpler. It just looks like psi double prime equals xi squared times psi. Now I claim that in this region, this equation is solved by two functions, which are given here, e to the plus minus xi squared over 2. Now it's solved in the following sense, that if I take this form for the wave function and I proceed to find its second derivative, what I will find is what is written here, which is to say I start with a function, I differentiate it once, and if I differentiate twice, I get this combination of terms. One of them is xi squared times the function itself, which is what I want to solve this differential equation up here. But the second term is present, but it's much smaller than the first term, because the first term is multiplied by xi squared, and by assumption xi squared is very large. So I can basically drop this term. So what's going on here is that I'm constructing an asymptotic solution, which is in these outer classically forbidden regions, and the asymptotic limit is that I'm looking at xi going to infinity, and in that limit I basically have a solution. The solution is asymptotically correct. Anything that it doesn't quite reproduce upon differentiation is smaller than the term that I keep. So you might wonder why my asymptotic form in the classically forbidden region is a Gaussian as opposed to an exponential, and the answer to that is that our earlier analysis, in which we talked about exponentials, held when the potential was a constant, and now of course v of x minus e is not constant. Instead, v keeps getting bigger, so the local decay length simply keeps increasing as I go away from the origin, which shows up in the Gaussian dependence, which is much faster than the exponential dependence. So now that we figured out how the wave function is going to behave very far from the origin in the classically allowed region, we can use that to try and write the wave function in what seems like a more promising form, which is we factor out the decaying Gaussian that we want and hope that it's multiplied by a function which is slowly varying at large distances compared to the Gaussian, and it's this function h that we will now try and find. So if we simply plug this in to the starting differential equation, we get a differential equation for h, which is written here. It involves the second derivative, the first derivative, and then a term linear in h. Now, it may seem immediately that this is somewhat more complicated than the equation that we began with, which I remind you is up here, in which I can take out the stuff that I had crossed out, put it back in. So the equation for H looks somewhat more complicated, but on the other hand, I expect that if I have the asymptotic dependence correct, H will be a simpler function. Indeed, we will see shortly that H will turn out to be a polynomial, which indeed is a simpler function. Now, before we get to that, we will simply try and solve this equation by imagining that we have a series expansion about xi equals 0, and so this is the so-called series of Frobenius method, in which I simply assume a series expansion and then plug it into this linear differential equation and see what I get. Now, what I'm going to do is, in each of the three terms in the differential equation, I'm going to plug this in, and then from each of the terms I will collect the coefficients of a given power of xi to the j. So that's what I've done in this line below, and let's just see what happened. So there is a term multiplying xi to the j, which is j plus 1 times j plus 2 times aj plus 2. Okay, so how did that happen? Well, if I go back up here and look at the first term, I take two derivatives of the series for h, and what that means is that if the starting series has a term which is needs to be 2 more than the term with which I want to end up. So I have to start with the term xi to the j plus 2 in order to end up with something that looks like xi to the j, but the xi to the j plus 2 comes multiplied by aj plus 2 according to this equation right here. So that's why I have an aj plus 2, and since I've taken two derivatives of xi to the j plus 2, I get one factor of j plus 2 the first time and a factor of j plus 1 the second time. Likewise, from the second term, I've taken one derivative with respect to xi and multiplied it back, and so what that does is it gives me back the same power of xi to the j, hence an aj. On the other hand, I began with xi to the j, so it pulled down a j before I multiplied it and fixed it back up. And the last term simply gives me a constant multiple of aj, which multiplies xi to the j to begin with. Okay, so what must be true is that this series in this down here has to represent the function 0, and therefore each of its terms must vanish. So that actually gives us a recursion relation between aj plus 2 and aj, and that recursion relation I've written here explicitly. Aj plus 2 is 2j plus 1 minus k over j plus 1 times j plus 2. Now the way we can use the recursion relation is if I know a0, I assume it has a certain value. According to this recursion, it will give me the value of a2, which will then in turn fix the value of a4, and I will get the entire set of even coefficients fixed by the starting value of a0. Likewise, if I assign a1, that will fix for me a3, a5, and so on, all the odd coefficients. So in this fashion, I will construct a solution which looks like a0 times an even function of xi, because it will involve only the even powers, and a1 times an odd function of xi, because that will involve only the odd powers. So it's clear that I have a two-parameter family of solutions, and of course I can think of this as linear combinations of an even function and an odd function in general, although we'll see that only one of the two will be realized for a given eigenenergy, but that is to come. Now at this point I have naively an infinite series at each value of energy. Okay, so I know that something must be wrong. I do expect to find discrete eigenvalues for which the procedure is sensible. So the sensible part has to do with making sure that when I'm done with this series and I combine it with the Gaussian that I had hived off earlier, I get a normalizable wave function. So for that I need to understand the asymptotic behavior of the function h. So to that end, let's think about what this recursion relation is doing at large values of j, so late terms in the series. So here is a recursion relation again. aj plus 2 is 2j plus 1 minus k over j plus 1 times j plus 2 times aj. Now if j is very, very big, so I'm looking at the millionth term in the series and beyond, then this will actually look to a good approximation be just 1 over j times aj, and the approximation will get better and better as j gets bigger and bigger. So now let's imagine that we take this to be the defining property of the recursion relation. Now you might object that at small values of j this is not true. That's true, but to any, even if I go up to a millionth term in j, to get this recursion relation to be very accurate, the first million simply constitute a polynomial, and my worry is that the infinite number of terms that are coming after j might give me some behavior that I should fret about. A polynomial multiplying a Gaussian I would actually be quite happy with, because at large values of xi the Gaussian will simply kill any polynomial no matter how large. So this is a fancy way of saying that examining the asymptotic terms in this recursion relation is sufficient for the purposes of deciding the asymptotic behavior of the function h of j. So this asymptotic recursion relation can be solved, and here is the solution. It just looks like c over j over 2 factorial, which means the function h of xi. So for example, imagine that I started with a naught, looks like a something proportional to the sum over j even values of j, xi to the j over 2 factorial. This can be rewritten, instead of summing just over even j, I'm going to sum over all j. So I basically just replace, send j to 2 times j, and I get this series expansion, which is of course a well-known function. It's simply the exponential of xi squared. So what I've discovered here is that if the recursion generically is going to give me a function that behaves like a Gaussian at large distances. So if I put it together with my old Gaussian, since that was e to the minus xi squared over 2 and this is e to the plus xi squared, I'll find that my wave function actually looks like e to the plus xi squared over 2 at large distances, which of course was the solution I discovered earlier. That was the growing solution at infinity. And what I've discovered is that generically I'm going to get back to the growing solution. Now this is okay. Remember that we only get eigenfunctions, normalizable eigenfunctions, if we choose the energy extremely carefully. Generically, if we begin at some energy and start integrating, we're going to find that the growing solution comes in. It's only when we cancel the growing solution that we will get a normalizable eigenfunction. So the fact that just because we had formally factored out a decaying solution doesn't mean that the function has been forced to behave like e to the minus xi squared. That only happens when I choose the energy correctly. So I haven't done that at this point, and so I get back the generic growing solution. So far so good. But in this language, if I want the function h to not grow in this fashion, the only way I can do that is to make sure that the series does not go on forever. So if the series is not to go on forever, then this recursion relation here simply has to tell me at some stage that aj plus 2 is 0, and all subsequent terms then will be 0 by the same recursion relation. So I need this recursion relation to give me 0 at some stage, and the only way that can happen is if the numerator is 0. So let's come down here. So for the series to truncate, I'm going to get that 2j plus 1 minus k is 0 for some j, and let me give that j a name. Let me call it n. Now this j isn't necessarily even or odd, it could be either. It just depends on, in my recursion, whether I start with an odd number, whether I pick the odd series or the even series. Okay, so from this vanishing, I learned that k in fact has to be an odd integer, and n has to be bigger than or equal to 0, as you can see, because j has to be bigger than or equal to 0 to begin with. So going back to the definition of the energy, putting back in the units and the factor of 2, I discovered that the energies, the allowed energies, must be n plus a half times h bar omega. Now I can use this logic to actually start to write the eigenfunctions. They're all going to look like polynomials times the Gaussian. So for instance, for n equals 0, I start with a naught and the series truncates immediately. So the function h is simply a constant, and therefore the ground state wave function, the lowest energy wave function, which has energy n plus a half h bar omega with n equals 0, which is to say energy 1/2 h bar omega, has this form, which is pictured here. It's just a Gaussian. For n equals 1, I start with an odd series with just a1, but the next term is 0, and so that just looks like a linear term multiplying a Gaussian, and that's the odd wave function that I've sketched to the right. For n equals 2, I get the next even wave function, which once a0 is specified, it gives me an a2, which is minus twice a0, and then it truncates. And so the function h2 looks like that. I multiply by Gaussian and get this function that I've sketched here. These polynomials, of which I've constructed the first three, have a name. They're called the Hermite polynomials. So the little hn of xi that I would write is actually proportional up to a number, it's a number times a certain canonical definition of what I'm going to call capital H sub n of xi, which is the textbook definition of the nth Hermite polynomial. But that's just a number times the functions that I'm calculating. So it means that the nth wave function is the nth Hermite polynomial times the Gaussian. And then when I normalize correctly, so demand that the integral of psi squared be 1 from minus infinity to plus infinity, I get this more complete form where here's the normalization constant, which is n-dependent. That's the piece of the wave function we just discussed. And xi now is to be written as m omega over h bar times x, so that you can check that integral dx of psi squared is equal to 1. So you're integrating over x, not over xi, because that's the appropriate physical unit when you go to actually normalize the probability. Okay, so at this point we're pretty much done solving the eigenvalue problem. We found the energies, which are n plus a half times h bar omega, and we found the corresponding eigenfunctions, and they consist of two series of polynomials times a Gaussian, polynomials which are even functions of position and polynomials which are odd functions of position, and together they form the Hermite polynomials. Now of course you know that eigenstates are stationary, so the probability distribution in any of these eigenfunctions that we've calculated is independent of time. But on the other hand, if we make superpositions of them, they will show oscillatory behavior, which will remind us of the harmonic oscillator in its classical incarnation. So let's look here at a simulation available from Mathematica's website of the time dependence of different wave functions. So up here are the coefficients that multiply the 0th, 1st, 2nd, 3rd, 4th, 5th state. So you can see right now I have it set, so the only piece of the wave function is in its ground state, which is therefore an eigenfunction. So here I start its time dependence, and what you see is a change in color, which represents a change in phase. It is getting multiplied by time dependent phase, but its amplitude squared obviously doesn't change. The probability distribution remains completely unchanged. So now let's go up and change the mix. So for example, I'm going to switch on the first wave function, the first excited state, and make a linear combination of them. So now you see that at this moment, which is some random time, so let me take it back to 0 in these units, I have some double humped probability distribution which comes from superposing the 0th and first excited state. And now let me evolve them. And when I evolve the superposition, you see that because of the phases changing at different rates, the probability distribution actually changes in a way that certainly starts to resemble the motion of a classical harmonic oscillator. Something is sloshing back and forth at a given frequency.